Welcome to another RDWorks Learning Lab. Today's session is going to be a further exploration into photo engraving. Now, by photo engraving I really mean dithering, dots, all those sorts of things that we've touched on before. But it's been a few months since I produced the Rust formula for photo engraving, and since then I've acquired more knowledge, and there are a few more variables that we need to take into account over and above the essence of what I wrote down in that formula. Now, the whole principle of that formula was based upon trying to understand how you could get a single black dot down onto your material. Now, it took a certain amount of time for that black dot to appear down on your material after the controller had said, I want a black dot. It had to pass through the high voltage power supply and then change the power to the beam to burn a dot on the paper. So there was a train of events that took place that took a finite amount of time. A typical specification for a good quality power supply says that it will deliver 90% of the demand power in less than 1 millisecond. Now, what that means is if we ask for it to deliver, for instance, 90% power, within less than 1 millisecond after the controller sent the signal out, it would raise to 81% as opposed to 90%. But 81% is still pretty good. So that's a typical specification for a power supply, quick acting. A millisecond in electronics time is a bit like a year to us. It's, relatively speaking, slow. Now, it turns out that these machines have all got different quality power supplies in them. My China Blue, for example, has got a response time of around about probably 2 or maybe even as long as 3 milliseconds, which is why my Rust formula says you should be using roughly 3 milliseconds to assume that you're going to get a good solid black dot. Not so with this machine. This machine is probably performing to the 1 millisecond standard. But one of the first things that we're going to do today is we're going to check what the performance of the high voltage power supply is. And we can do that with a simple test. Today's going to be quite a busy day because as well as looking at the power supply response time, we're going to look at the different colour that we can burn onto different types of material. Now, I know that sounds strange. If we've got an organic material, basically all we can do with an organic material is burn it. Now, if you burn it a lot, you finish up with pure black carbon. If you burn it a little, you finish up with a faint scorch mark. Or, as I have found out, almost nothing. So you can actually produce an impression on this paper without actually making any coloration. Now, it depends on the composition of the material, the organic material that you're working with. And it's something which I discovered that caused me a little bit of consternation, because it does mean to say that my little dot pattern doesn't always give you the results that I expected. When I did my formula, I was using this thick card, which is 480 gram card, quite heavy card, but it's a pure pulp card. I'm sure most of you have been into pubs and bars and you've seen beer mats. Well, that's effectively what this material is. It's basically sponge-like card, but it is basically a nice uniform type of wood, effectively, without any grain in it. It's wood pulp, pure wood pulp. But as I did some more work with other cards, I realised that my little dot test was not giving me exactly the results that I expected. So today we're going to take a look at a range of materials. We're going to take a look at a range of lens focal lengths. We're going to take a look at a range of speeds and feeds to try and find out what the best combination is for getting good contrasty pictures onto an organic material. Now, over the past several months, a guy has been developing an alternative piece of software to RDWorks, and at the moment it is a work in progress, but it is a work that's fairly well progressed. So you can go to lightburn.com and you can download a 30-day free trial of the software. But I particularly want to use it at the moment, not for some of its quite interesting features that he's built into it. It's a great piece of software which, when it's finished, it will be light years apart from anything else. And the photo engraving element that he's built into this software is very, very interesting and worth a second look. So that's what we're going to be using today. We're going to be using his piece of Lightburn software to generate some pictures and some tests. I'm going to use this Lightburn software to produce my first test program. And basically what I've got here is two rectangles. The blue rectangle around the outside is going to have a cut line. I'm not planning to cut through the material, but I want a scorch line around the outside. And then this inner rectangle is basically going to be scanned with a series of lines from opposite directions. And you'll see what happens when we look at these under the microscope. Right, so at the moment I've got a 1.5 inch lens set up in here, and we'll just run that little test program. Now, before we go and look at this under the microscope, I just want to remind you of something that we've tested before. So what we've got is a constant power beam here. There was about 55 watts coming down through the nozzle, but we didn't actually have the nozzle and the lens on. We took the nozzle and the lens off, and so basically what we had here was the unfocused beam. And it was running at 15 millimeters a second, 20, 30, 40, 50, 75 and 100 millimeters a second. Now, as you can see, as the speed increased, so the width of the line decreased. I just want to bring that to your attention, because what we're going to look at under the scope now, we'll be able to see the focus beam does exactly the same thing as this unfocused beam. Now, in the light of our observations about the way in which speed affects line thickness, I hope you'll see that round the outside here, the line thickness at 200 millimeters a second is substantially wider than the line at 400 millimeters a second. That's observation number one. Now, observation number two, as the beam starts slowing down for the corner here, you can see the high density center part of the beam coming into effect, and as it slows down it's burning deeper and deeper, and it's producing, well, I don't know whether it is producing black or whether it's just the fact that it's hiding inside a very deep groove that appears to be making it black. But the one thing that we can see is that as the beam slows down, it gets even wider at the corner here. If we take a look at these 400 millimeter second scan lines, we will see not only have we got a central dark furrow, we've also got a shadow line around the outside, which basically is, if you like, very, very light burning that's taking place. It's engraving that's causing a depression, but it's not actually causing any colour. Now, for some reason or other, we can see that the beam is a bit intermittent here, and as the beam power drops off, look, we've got virtually no coloration there at all. Now, the whole purpose of this pattern was to look at this particular feature here, the ends of these lines that are not lined up. So this is the start of one line, and this is the return line. And as you can see, they do not line up at the ends. So consequently, when we do a nice clean pattern, we're going to get some sort of offset between the lines. And this is called a scan line offset. It's not backlash in the system. It's basically all to do with the response time of the high voltage power supply. So when the signal switches on, there's a delay in the signal starting. And the way that I've designed this pattern, the edge of this line is basically 0, where this line should start and this line should finish. And if we look at the other side on this second line down, and we've got exactly the same pattern at the other end, where the lines are offset relative to each other. So if we take a look here and we measure this gap from here to here, these are 0.1 divisions, as you can see, 0.1 millimeter divisions. So we can quickly check here, and we can see that we've got roughly, let's just put that line on there,
about 0.2, maybe 0.25 gap there, which is about right because the lines are themselves about 0.2 wide.
Now what we've got here is not an exact science, but it's an estimation that enables you to get an idea of what your power supply, your high voltage power supply, is capable of. Now we know that we were running at 400 millimeters a second with our test, and we found that we were getting a 0.2 offset between the lines. So in 1 second, 1,000 milliseconds, if we divide 1 second by the speed, 400 millimeters, we find that we take 2.5 milliseconds to travel a millimeter. So if we know that we've got a 0.2 millimeter offset, we can say that 0.2 millimeters by 2.5 milliseconds per millimeter gives us a delay time of 0.5 milliseconds. The specification for a reasonably good power supply is that it is less than or equal to 1 millisecond to get to 90% of the target value. And it certainly looks as though we've got a power supply here that's capable of doing that. So for the purposes of the Russ formula, for this machine, we could probably use 1 millisecond. Well, as we go further into it, we'll see just how good this machine actually is and whether it's capable of getting to 0.5 milliseconds. Well, okay, so we're going to work our way through the Russ formula at the moment and do a little bit of modification as we go. So the first thing is we are going to be using a 1.5 inch lens to start with, and basically it really doesn't matter what size lens we go for. It's either going to be a 2 or a 1.5 inch. We're always going to finish up with about a 0.2 millimeter diameter dot. So that means the best resolution picture that we're ever going to be able to achieve is about 127 pixels per inch. We might be able to push that up to 150, but we're going to start off with sticking to the rules, which is roughly 127 pixels per inch. So if we've decided that we can't have a dot size any less than 0.2 millimeters, it means we're going to get roughly 5 dots per millimeter out of this machine. Now the crucial part of this formula is this element here. It's basically the response time that I got by empirical means, by trial and error. But now what we've done, we've found a simple test that enables us to determine that, for instance, this particular machine, we probably can use 1 millisecond, not 3 milliseconds, as the basis of our ongoing formula. So having decided that we can use 1 millisecond per dot, as opposed to 3 milliseconds per dot, we've still got the same dot size, 0.2, which means we get 5 dots per millimeter. It means we're going to take 5 milliseconds per millimeter, and as there's 1,000 milliseconds in a second, if we divide that by 5, we shall finish up with a speed of 200 millimeters per second. So we can run this machine at 200 millimeters a second and still expect to get single dots. That's what the prediction says. So we're now going to do our little test pattern, and we're going to run our test pattern at 200 millimeters a second, and we're going to work with about 15% power for this machine. We're going to vary it up and down a little bit. We're going to find the best combination of power that goes with this speed, provided we can see all the pixels coming down at this speed. If we can't see the pixels, then we shall have to lower the speed, and it means that I've got my estimation wrong for 1 millisecond per pixel. Okay, now as I said to you, I'm not going to subject you to the trauma of going through all these dot tests, but here I've got 3 different types of card. I've got some sort of a yellowy card, which is a nice smooth card. We've got some lovely white card here, which is a hard surfaced white card, and here we've got this what I call beer mat material. This last material here is about 1 millimeter thick, because what I'm finding is that when I'm using these thinner cards, this one is only 0.2 and this one is roughly 0.3. With these thinner cards, it's very easy to burn right through the card. And that's not what we want. Ideally, we want to burn on the surface of the material and just scorch the surface by various degrees. But as we found out when we were trying to check how to do that, it's very, very difficult. The only way that we could do that is having a very long focus lens set out of focus. And of course, as soon as we do that, one big problem. The dot size gets bigger, and that's going to make our pictures look horrendous. So we're looking for the finest dot that we can get and the blackest dot that we can get. And now the trick is, how do we do that? I've done some experiments here already with my little dot patterns, and we'll go and look at these under the microscope and just do a few comparisons, and we'll talk about the results.
Well, this is our 0.2 thick yellow card, and it's set to 18% power. Now, as you can see, this is way too much power, because if we take a look at the top line there, you'll see that we've actually burnt right the way through. And what I've got is I've got a piece of white paper in the background so that you can see that it's burnt through and there's a white background. Now, also the center line of dots, although they're there, they're a bit vague. They're not really dark. And we can see that we get this special pair of dots that I've stuck right in the middle of the pattern here. Now, these have only got like one, I think they've only got 1 pixel space between them. So these are a rather special set of dots. I think they're 2 pixels long and they've got 1 pixel space between them. So these are a rather strange set of pixels right in the middle of this set of dashes. And these are pixels, 1 pixel, 3 pixel space, 1 pixel, 3 pixel space, and these along the bottom here, they're a pixel space, a pixel space, a pixel space. So the fact that we can't see any spaces means the dots are at least 0.2 millimeters diameter, and we can check that out with a quick look. And if we take a look at that bottom line there, I would say that we are 0.1 to at least 0.25 diameter. So this is a 2.5 inch lens, which is giving us quite a large dot. But we're trying this lens because we want the softest amount of power that we can possibly get, so that we don't burn through the paper. We only, if you like, colour the surface of the paper. So that's why I'm trying the 2.5 inch lens. So from 18% there, we drop right down to 13%, where things are a bit pathetic. Virtually no colour in that centre line of dots. We're getting a bit more resolution on the bottom line of dots. You can see that we've actually got a dot pattern, but it isn't dark. It's nothing like the colour of the dashes on the top. So let's increase the power by 1%. And here we are at 14% power. Now you still see that we've got far too much power on the dashes because we're cutting through them. We're right through the paper and you can see the white background. So we go up to 15%, where we'd expect to find even more cutting. Yeah, we get more cutting and we're getting a little bit more colour into that bottom line of dots. But to be fair, they're still pretty pathetic. Now here's a direct comparison between the yellow card and the white card. Now here's a classic example of what I mean about different coloured dots. These are done at exactly the same speed and exactly the same power and with the same lens. Why has all the colour disappeared from that centre line of dots? Why aren't they brown? Well, the answer is it's all to do with the composition of the paper itself. The white paper is a higher quality paper with quite a lot of kaolin in it. Now they use kaolin or china clay to dress the paper to make it nice and shiny. If you go to glossy catalogues, they have a huge amount of china clay in them, but this has got a percentage in. But even so, that percentage is completely destroying the burnability, if you like, of the organic fibres that are in that material. And so consequently, we're not getting very much scorching. We're getting some depressions there, but we're doing something with the china clay itself. As you can see, when we allow the power to stay on long enough with the dashes, we can create some colour. But even so, it's a bit of a strange colour, because if you look around the outside, you'll see, particularly on those two special dashes in the middle that I was telling you about, look, they've got no colour. And we can see the halo around the outside, where there probably should be burning. If we look above at the yellow paper, you can see the halo around the outside of the dark burn is dark brown. Well, we don't have a dark brown halo around these, and certainly that centre line of dots and that bottom row of dots are colourless. I mean, we thought the top one was pretty bland and weak, but this white paper, which you might expect to give a much better quality dot, is in fact rubbish. What you're now seeing is my beer mat paper at the bottom. This is the thicker card. These are exactly the same settings, 2.5 inch lens with 15% power. And, well, you know, as you can see, that centre row of dots is even more pathetic. But the top row of dashes are quite nice and crisp, because this is a much thicker paper. We're not burning through it this time. So we can afford to put the power up this time. And so we go up from 15% to 17%, and we're getting a little bit of colour into the single dots at the bottom, and we're getting a little bit of colour into the dots in the middle as well. We go up to 19%. The top row of dots are getting better. The middle row of dots are still pretty pathetic, and that bottom row of dots, well, we're getting a little bit of colour in there. So we go right up to 20%, and well, we're gradually introducing a little bit of colour in there, but not a great deal. So we push it up to 30% power. We're really not doing a lot, are we? We're making the top line darker and thicker, and we're making the bottom line a blurred set of dots that run into each other. It's pretty poor. So this 2.5 inch lens is not doing a very good job. Let's swap it to a 2 inch lens and see what we get. Now again, we'll use our yellow card as a comparison, and here's what the 2 inch lens looks like against the 2.5 inch lens. Same power, same speed. Much thinner lines, very dark. The centre dots are, they're beginning to show in the centre as dark, but round the outside they are, again, very pathetic. The bottom line of dots are beginning to show up as single dots. So it is quite promising. If we look there, we're finding that we are able at 200 millimeters per second to see single dots. They're not blurred into each other. So we seem to have the speed at 200 millimeters a second and the response time at 1 millisecond about right. Otherwise we wouldn't be able to see those single black dots along the bottom. So let's push the power up a little bit and do some more comparisons. Now we're getting some colour into the single dots in the middle. We're at 21% power. Now we go up to 25% power, and we've lost the single dots at the bottom, and we're getting a little bit better on the dots in the middle. As we're getting more power, we're also getting a thicker line. We compare that to that one, and they're nearly the same. The top one has 15% power with a 2.5 inch lens, and the bottom one has 25% power with a 2 inch lens. Not very good results, either of them. Let's have a quick look at changing the lens again to a 1.5 inch lens, and we keep the power the same at 25%. That's something different, isn't it? Look at the crispness of the dashes. We've got positive single dots along the middle, and we've got a pretty good approximation to single dots along the bottom. they're running into each other. But overall, if we take a look at the dimension of those dots, we should probably find they're no more than about 0.1 or 0.15. You see, we're down to 0.15 now for a dot size, which is very, very promising. We could even be, yeah, if we look at those dots at the bottom there, single dots, they could well be nearly 0.1, maybe 0.15 optimistically. But that's certainly the best configuration that we've come across so far, and that's using this thick card. Now the thick card does mean to say that we can burn in without burning through, because we've got some depth there. So that bodes well for, you know, if you're engraving into plywood, then yes, you will get a good contrast between a dark burning dash and a dot. But the key thing is we're able to do this at 200 millimeters per second. That's 3 times faster than I was able to go with my China Blue machine. The point I'm making here is it's quite important that you assess what the capability of your machine is. You can't run faster than the machine's capability. And if your machine is a 5 millisecond machine, so be it. It's a 5 millisecond machine. You'll have to base your calculations on 5 milliseconds. So we're getting the most contrasty dots from this super thick card that I bought from Amazon. And this is what I should be using for all our comparative engraving tests. Well, here we are close up with the Lightburn software that we're going to be using for our generation of pictures. Now I'm using this software because it's got some extremely good features with regard to photo engraving. First of all, a nice feature that we've got down here is I can set up either of my machines as a device, and when I call up for instance the Lightblade machine, which we're using at the moment, it will auto change all the settings for the Lightblade machine. So I can draw for the Lightblade machine now without having to go back into config and change everything. Now it's got a similar feel to it to RDWorks, but I'm not going to go into it today. But there are lots of very nice features in here. The user interface is a lot better than RDWorks. We're just going to use it for the benefit of the photo engraving today, and I think it's possible that at some stage in the not too distant future I should be generating a little short series dedicated to understanding this Lightburn software. As you can see at the moment at the top here, it's still a beta version, but it's rapidly becoming a fully fledged competitor to RDWorks. So the first thing we're going to do is to import this picture of the tiger. As you can see, it's a coloured picture. I've got no idea what resolution it is, but it's probably not a very high resolution. As it comes in, it automatically strips out the colour. I'm going to change the size to 150 millimeters wide. The padlock is automatically locked to give you control of the aspect ratio. So I'm going to make it 150 millimeters wide. And that's all we're going to do to it really. As you can see, as it's imported it, it's automatically selected as a scan layer. It doesn't say that it's a bitmap as it does in RDWorks, but if you try and change it to anything other than a scan layer, you can't. So the same effect is there. Now it comes in with some preset settings, but we can quickly change those. In this particular instance, we know that we're going to run at 200 millimeters a second. We're going to have output, yes, and we're going to have air assist on, no. Now the power, I think we decided we were going to use 25% power and 25% power. Bidirectional scanning, yes. Negative image, no. Overscanning, no. Now here we've got line interval and dots per inch, PPI. One of the great things about this software is you don't need to worry about the line interval when you're doing photographs, because you choose the resolution here, and let's just say we decided it was going to be 127, and you'll notice that automatically it sets the line interval for you. Number of passes, well, we're only going to do one pass. Now here we've got, and this is the reason why I'm using this software, we've got all these various options here for dithering. Now the one that we don't want is the one at the bottom, which is grayscale, because that's not dithering, that is exactly what it says. It's grayscale for 3D engraving. But we've got these other 1, 2, 3, 4, 5, we've got 6 other options here which we're going to test. Well, we're not going to test all 6 of them, because this one here, threshold, is just black and white. Anything that's lighter than mid-grey turns to white, and anything that's darker than mid-grey turns to black. So this is a pretty basic, it's not really dithering, it's just a separation. But the first one that we're going to check is something called ordered. So we'll ask for ordered, and here we get a typical example of what ordered means. I'm personally going to ignore the comments at the bottom there at the moment, because we're going to test and find out which of these works best for us. Now 127 pixels per inch is what we said we were going to do, because that was the dot size. So basically what I'm going to do now is to run this program as an ordered dithered picture, and then I'm going to come back in and I'm going to, one at a time, choose these various options down here, and we're going to generate a series of pictures. Now you don't need to be involved with the donkey work of me just laboriously printing out these pictures. So we'll come back when I've done the pictures, and we'll take a look at the results and compare the differences between these various types of dithering. Now I've chosen this particular picture because if we look down here, we've got some fine hair detail down the side here. We've got lots of good contrasty black and white stuff around the face here, and we've got lots of mid-greys around, plus we've got these white whiskers here. So there's lots of detail, particularly around this area here where we can see the black dots where the whiskers sit into the face there. Delicate pattern shading at the top of the nose. There's all sorts of things that we can use to reference and compare these various picture qualities. This software at the moment does not have any picture adjustment facilities, but as I understand it, for the future there will be brightness, there will be contrast, there may even be cropping. So yeah, watch this space. So it's great having this software here, but you must remember that before you even start looking at these pictures and these various types of dithering, you've got to sort out the dot quality for the material that you are using. So if you live in a rainforest, there's no point in building a house with paper mache bricks. You need the right stuff to do the job. And that's what we do here with our black dots. We're choosing all the factors that get us the darkest dots for the material that we're using. And if you can't get dark dots on the material that you're using, then don't waste the material. That's my basic advice.
Well, there's our first picture. It's the ordered picture. The only problem is I have forgotten to correct the scan line offset. 200 millimeters a second, and let's see what we've got. Let's just get you looking through my little spyglass there. And I think you can see that we've pretty well fixed the line offset. It's more or less lined up now, and that was with just a 0.02 offset. Now, in essence, these pictures don't look too much different on the surface, but because of the very complex and detailed way that the dots and dashes are arranged, a 1 pixel shift, which is 0.2, is going to make quite a lot of difference to some of these patterns that exist on here. It's not immediately obvious, but for instance, if we look down here at these patterns here, we'll find that the pattern down here is not quite the same as it is down this one. The combination of dots and light spots is different. When you move some of the dots by as little as 0.2, there are places down the side here where there are differences that are slightly more obvious. It does make a difference to have the scan lines lined up. So let's push on with some more pictures of a different So let's push on with a different dithering pattern and see what we get.
Well, this one here is Jarvis. This one here is newsprint. We will look at these under the microscope and do a little bit of a detailed analysis of the dots and that. I think this Jarvis one is actually overall the best from what I've seen so far. What we're going to do now is to rely on the information that we looked at under the microscope. We did all our drawings so far have been done on the basis of a 0.2 dot. But we thought it was possible that we could get down as little as maybe 0.15 millimeters for a dot size. So if we go back and rework these calculations, we'll find that we finish up with the possibility of pushing the picture resolution up to 170 pixels per inch. So we're going to do that. The next stage is, with a 0.15 dot, it means we've got 6.7 pixels per millimeter. Now, if we look at 6.7 pixels per millimeter in this equation here, we'll find that we finish up with a speed of 150 millimeters a second. So we've got 170 pixels per inch and 150 millimeters per second. Now, there could be an argument maybe for reducing the power a little bit because we have reduced the speed, but I'm going to leave the power set at 25% and see how that reacts. Technically, I should go back and do my little line test again, but I feel moderately confident that we're not going to have a major problem. And we're going to compare the slight increase in resolution to see whether or not it makes any significant difference.
That's the Jarvis 127 pixels per inch. Because we've got a higher pixel resolution, there's going to be less background and more black dots. So I'm expecting the picture to be slightly more contrasty, darker. And it certainly looks that way at the moment. And sure enough, that is a remarkably good image. On this spare piece of white area here, I'm going to put down what RDWorks would do with exactly the same picture, with exactly the same parameters. And we'll see how they compare. That's a big difference, isn't it? I did mention earlier in the video that this particular software, as at the moment, doesn't have brightness or contrast controls. Well, RDWorks does, but you can see why RDWorks needs it. Whatever the guy has done to this software, bearing in mind these are exactly the same parameters, exactly the same material, exactly the same lens, everything about these two pictures is exactly the same, but they're not the same result. So the dithering pattern on here and the background control of the way in which the dots are placed down is completely different. This one would require brightness control, maybe some contrast as well. This one doesn't need it, it's one-touch software. So, I mean, you can see the results for yourself. This is 10 out of 10, this is work in progress. All I can say is that on the basis of these results, I shall never be using RDWorks for photo engraving again. I shall put all my faith into Lightburn. But we will go and look at them closer under the microscope to see just why these differences exist. Now, I'm having to stick this card down with magnets because, as you can see, it's a little bit curved and I obviously can't afford to have it sticking up at the edges. So we're putting the centre downwards and we're clamping the corners. I mean, from a distance, they all look pretty good. I mean, that's the ordered one. That looks particularly nice. That's the Atkinson. I mean, I can see that there's a big contrast between this one and the Atkinson. The Atkinson one is a lot crisper around here. But then again, it has got just a hint of 3D-ness about it. Here's a Jarvis. I think on balance, the Jarvis is better
than the Atkinson. If we take a look up at this corner here, there is definitely some sort of strange patination that's going on up there, whereas here it's much more random. And then we've got this one here, which is newsprint. Well, yeah, from a distance it looks okay, but close up it looks exactly what it is, very, very, very dotty and blocky. Now, here's our Jarvis with 170 pixels per inch, an increase in the resolution. And this is a really, really nice picture. It's almost like a good sepia photograph. And this one here, which is the RDWorks one, well, to be honest, that is very brown and burnt out. It is, you know, to be honest, it's just totally too dark. And then finally, what I've done is that. Now this one looks remarkably good, but the only reason it looks remarkably good is because it's twice the size of that one. Still got the same resolution. In other words, there's still the same number of dots per inch, but because it's a bigger picture, your eye seems to see it almost as twice the resolution. The resolution is the same, but it's because the picture is bigger, the dots are relatively a smaller part of the picture overall. Well, this is the ordered one. And observations, well, the lines are very black and the dots are nice and clear and single. They're not blurred and running into each other. So at 200 millimeters a second, we're definitely producing clean dots. They're not as dark as the lines, but at least they're there and they're not bad. When we look at this from a distance, it does look a bit like a tapestry. It's not a particularly pleasing picture to look at close up. You have to stand quite a long way off and then it starts to look half reasonable. This next one is the Atkinson, and that's the eye of the tiger. Now the dots that you can see are truly there. There are no invisible dots. You'll understand what I mean by invisible dots when we talk about one or two others later. So this is not bad. Look, we've got lines that are joined. We don't have any white between the solid lines. They're nice and just joined up. So the pitching is absolutely perfect. And in general, this is not bad. This one is the newsprint, which is weird. Clean, but weird, because there are no dots in here. There are only lines. Oh, look, there's one or two little dots there. And then here we've got the Jarvis. Now, Jarvis is actually quite nice. It's probably one of the best ones that we saw. And the lines are nicely buttered up against each other. There's no white gaps in there, so the pitching is perfect. When you look at them in normal light, as opposed to under the microscope here, some of those dots look as though they are basically little white depressions rather than actual black dots. We know that it can make nice black dots because we've seen it on some of the other dithers. This was the standard Jarvis at 127 pixels per inch. So what we did was to push the Jarvis a little bit harder, and we thought that we might be able to get it up to 170 pixels per inch. So first of all, we need to take a look, see what we've done to these lines. Well, the lines have definitely not as clean. They are more overlapped. We've got some strange patterns there now. If we take a look at some of these dots, you'll see that they are actually touching each other. So it's possible that this actually might be, although it doesn't look like it with the lines, with the dots it does look as though we've got the right pitching. This is the very large picture, and sure enough, there we are. We've got exactly the same arrangement here. We've got lines that touch. They just overlap each other, so they're not so obvious as individual lines. This is the same image on the white card, and we're seeing more of the lines coming back into play, but we're also seeing a lot of these grey dots that actually aren't dots at all. They just look like dots under this light, but in reality when you look at them in daylight, they are nothing more than depressions in the surface of the material. So surprisingly enough, this was quite a clean looking picture. This is RDWorks. Well, just about enough white there to show you that there are some whiskers there. And then let's compare that to the Jarvis one. And you can see there's a lot more white on those whiskers. So something strange about the way that RDWorks is putting down the dots. The signals are not clean.
Well, here we are at the end of today's session, and I think what we've learned is that, first of all, before you start throwing dots at pieces of cardboard or wood or anything expensive, you must get your dots sorted out for the material that you're using. And that's what this formula does for you. So, as I've shown you, you need to adapt it and modify it depending on what you find your machine is capable of. So before you start throwing dots down, find out what your machine is capable of doing. Now, I do know that there are some machines out there that are just not capable of producing this very fine little dot pattern that I produce. If you can't produce that dot pattern, then don't waste your time trying to produce something on paper like this, because it won't work. You've got to have a machine capability before you have a photo capability. The second thing that we've learnt today is that I'm not going to be using RDWorks anymore for photo engraving. Give me Lightburn every time. It's so much easier, it's so much cleaner, it produces much better results without having to faff around with Photoshop or any of these other external programs. Now, as I mentioned earlier, Lightburn is still not a fully fledged piece of software. It cannot do everything that RDWorks can do. For example, you can't go in and modify your machine parameters at this moment in time. You can't go in and modify the vendor settings. They're features which are not, at the moment, included in that software. They will be, but they're just not there. So you will still need to run RDWorks for some features and Lightburn for the goodies. But hey, patience. There's only one guy developing this piece of software, and he's got another job as well. This is only a part-time activity for him, and he's done an amazing job from what I've seen so far. As I said, I'm not a salesman for Lightburn at all. Just credit where credit is due. Anyway, we can conclude with a little bit of a thank you for your time, and I hope to see you in the next session.